would, and in this video we're going to talk about root finding. Now when we think about root finding, what we're looking at is a function. So we can think of something as a function of x. So if x is our independent variable, the function gives us the y value, or our dependent variable. Specifically, we'll take this function as a value of x, and we're looking for where it crosses the x-axis, or where the y value, or the dependent variable, is equal to 0. Now, depending on the type of problem, this can range from trivial to fairly challenging. So, for example, if we have a linear equation, so here's a video of me throwing an object in the air and measuring the acceleration. The linear equation for that is actually fairly straightforward for the velocity. If I'm looking for the spot where the velocity is equal to 0, which in this case is when the block reaches the top of its motion, all I have to do is algebra. And in fact, if you wanted to go back and look at the video that deals with solving for a single equation with a single unknown, we take our function, whatever it is, we set it equal to 0, and then we're able to solve for the unknown, in this case the time when the velocity goes to 0. Or we can always plot it and look for where that plot crosses the x-axis. We can have another type of function, something like a second order polynomial, where x is raised to the second power, or squared. And when we have this case, we actually have a special equation for solving that. We can set it equal to 0, that's where we're looking for our roots, and then our quadratic equation will let us solve for the roots directly. So that's the negative b plus or minus the square root of b squared minus 4ac divided by 2a. Hopefully you remember that equation. If not, it's in our FE reference handbook. But again, we can plot this, and we can look at where that plot crosses the x-axis, where it passes through to 0. Alternatively, we can look at even more complex equations, and even though there's only one unknown, we can end up with scenarios where we don't really want to use algebra and the quadratic equation doesn't apply. And this can be super painful for us to work out. So we can ask ourselves, okay, can I use the linear equation, algebra? Can I just isolate the unknown? Can I use the quadratic equation? And if I can't do those, a couple of options. I can either guess and check. So we can just start guessing, working our way through that. Or I can plot the results and look for where it crosses the x-axis. Now, some things to keep in mind when we do this is that as engineers, we're not just doing math for the sake of doing math. We're doing math because it reflects reality at some level. And when we do that, we'll want to consider what is reasonable. And so we'll want to be able to identify a reasonable range of values for our roots based on the physical scenario that we're looking at. And then we can use other methods. So there's a whole field of study called numerical methods. One of the methods is called the bisector method, which is actually fairly straightforward and easy to use. I'll show you that here in just a minute. It's basically improved guess and check. But we can use these methods to solve our equations going forward. So let's look at an example problem. So in this example problem, we have a problem from statics. We have a system with two springs and a force being applied. This video shows a little scaled down model of this, in which we want to find out how far away from the wall the springs will stretch to generate this force. Now, when we draw our free body diagram and write our equations of equilibrium, what we're given is actually this equation of equilibrium, which is, needless to say, a bit of a doozy. And so our options, we're trying to solve the d that works all of this down to 0. So we can think about our procedure. So the first thing we'll want to do is we'll want to identify our approach. So we can ask ourselves, do we think we can isolate d as a single unknown in this equation? And I'll say for my part, that looks horrendous. Second thing we could use is the quadratic equation. I'm not even sure that this is a second order polynomial. In fact, I'm sure it's not, but I wouldn't even want to try to get it into the appropriate form. So let's not do that either. The next option would be, of course, to guess and check. So we're going to attempt that. Now the other thing to recognize is that we're not solving this in a vacuum. So our second step is going to be to estimate a reasonable range. And if we look at the system, we know that D can't ever be less than 0. So it's always got to be greater than 0 or in the positive direction. Now obviously this equation would give us a value if D were negative, but that value is not meaningful in the context of the problem. So this is where we have to work as engineers to identify what is reasonable. Furthermore, I'll argue that D really is probably less than maybe 3 or 4 meters, because if it were more than that, this system would start to look really stretched out, which is not what we've seen in the picture or in our physical model. So we've got a bit of a range going on here. Once we have that, we would go ahead and attempt to do some guess and check. And so the way that we would do this is something called the bisector method. We would pick a value at the bottom of our end of our range, and so I want to solve this equation, so this function, when the input value is 0. Now when I do this, I get a value of negative 175 newtons. This whole component goes away, and I'm just left with this answer. Now for the sake of conceptual clarity, I might start plotting my answers. So if I'm going to make a plot of this, I'm going to now put this value on my plot. So when my input value, my D parameter is 0, my output is negative 1.75, something like that. All right, let's try a different answer. Let's put 1 meter into this and see what we get. Well, when we put 1 meter in and we use our scientific calculator, we get negative 124 newtons. And so it goes about here. Now the interesting thing is we are actually moving toward the origin, the x-axis. So that's good, that's moving in the right direction, though it's not getting there very quickly. Let's go ahead and do 2 meters. When I calculate this at 2 meters, I get 161 newtons. This is exciting. 161 newtons. So we've now crossed the x-axis, or where our roots would be found. And so we can now start bouncing back and forth. So let's say I did right in the middle, 1.5. F is equal to 1.5 meters, or the function at 1.5 meters is equal to negative 17 newtons. So now I'm about here, getting real small. Okay, I could repeat the process. Maybe I split the difference between the two. I'm just going to start plotting them here. So 1.7 gives us an output of 46. So somewhere around here. 1.6 gets us an answer of 13. So again, splitting the distance. And then 1.55 gives me an answer of negative 2 newtons. So we're going to say that our answer, the function at 1.55 meters, is equal to negative 2 newtons, which we're actually arguing is about equal to 0. And so at that point, our answer is, our distance D is approximately equal to 1.55 meters. So that's following that process the whole way through. Alternatively, we could start looking at some different plots. So let's say that I have Excel handy. I can go ahead and plot this function. And if I plot it across the whole range, of course, we'll see things that aren't reasonable relative to our system. And so we might zero in again in this 1 to 2 or 0 to 2 meter range. And as we do our plotting of the data, doing that bisector method, kind of zeroing in on where the value is, we will end up with an answer of 1.56 meters. So we can keep repeating that process until we get close enough and we call it our answer. So again, just to review, our best approach is if we can use algebra, we want to use algebra. If it's a polynomial equation, we should use the quadratic equation to solve for it. But if it's more complicated than that, we can guess and check, and doing a plot using a tool like Excel is a really good idea. Here's your example problem looking at projectile motion. So an object thrown both in the x and y directions, and you're being asked to find where it lands. So I've given you the equation. You can decide if you can solve this with algebra, your quadratic equation, or if you need to guess and check. Look forward to seeing you on campus. Take care.